Hi everyone, and welcome to this live demo of Muk3D. I'll be presenting about the whole Muk3D suite. So that includes the three main products, which are Muk3D Formation, Muk3D Tailings Plus, and Muk3D Simulation, which is an add-on. Muk3D Formation is basically just the earthworks modeling component. So it allows you to do all the earthworks modeling, do some basic hydrology and visualization, as well as some scripting. Then Muk3D Tailings Plus contain all the components from Muk3D Formation, but on top of it, it's got all the parts around tailings deposition and raisings of the dams based on specific construction type, as well as doing some dam break analysis. And then finally, Muk3D Simulation, which is an add-on, now allows you to do sequential tailings planning. And it contains, it's an add-on that comes on top of Muk3D Tailings Plus. And it basically couples Muk3D together with Excel or GoalSim so that you can actually run some simulation and now do sequence of events that are happening. So I'm going to hop straight into it. This is what the interface looks like. As I mentioned, Muk3D is really powerful to do rapid design and volume calculation. So I'm going to start straight ahead, and I've got a grid that's loaded here, and I will start build a structure. And for that, I'll go to dam, draw a dam, and it will give me some information about what is the characteristics of that dam. So in this case, I will build a dam that is at 110 meters of elevation. It will have a crest width of 20 meters, and we'll put a downstream slope of 1 in 3, an upstream slope of 1 in 2. And I'll go ahead and build it. So you'll see that I just select what is my grid, and then I can just go ahead. And as I'm doing the drawing of my points, automatically my dam is being designed and drawn. So now I've got my dam, the dam wall that's been built. I've put my dam wall at an elevation of 110. This is a completely dynamic model, meaning that actually the structure that I'm seeing here can be edited. So let's say my slope, actually, I'm not satisfied with my slope. I want to actually have it as a slope of 1 in 4, and that will change my slope to 1 in 4. Automatically, the volume that is required to actually build this dam is calculated. So in this case, it's 1.6 million cubic meters with a footprint area of 308,000 square meters. I might want to change my the alignment of my dam. Might not be satisfied with it, so I can just change it, edit it, and automatically all of those characteristics will be updated. I might want to add to it. So this is a dynamic dam, a dynamic component. So all it does is it creates a dam from a center line, then it merges the dam into the grid. Maybe I want to add the pond to it so that actually we can estimate the volume within. So I'll just add to it. I'll select a point inside of my pond. And now it adds to it. So now I've got, because my crest is at 110, maybe I want to see, well, what's the volume if I've got like a 2-meter freeboard at 108 meters. And you see my volume of my dam is at 7.3 million. This still stays a dynamic model, meaning that I can edit it, I can change the alignment, and everything is still varying. All the characteristics gets recalculated. On top of it, I might want to maybe estimate what is my stage storage curves. Maybe I want to reuse that as part of my water management. So like for me, that's definitely something that I would do quite often. So I might say, actually, I want to estimate up to 110 meters. Every single meters, what is my area versus volume versus elevation. So I'll take a point in the grid, and then it will go ahead and calculate for each of those various elevations. So you can see here, it went and calculated 98 meters, 99 meters, etc. And it automatically created a file called basin.ccurve. So I'm going to open this. And as you can see, it calculated the different slices for different elevation. What is the volume for each of those slices? What is the total volume? What is my plan area? And I can reuse that as part of another. Maybe I'm doing some modeling for in terms of water resource management, and maybe I need to have that information. And that's something that you can use automatically. Now, all the data that you're looking at here, it's in Muk3D format. However, you can always export some of those data to other formats. So maybe I want to get the break lines out of that dam. So let me just hide. I might want to just save this. Hold on. Let's see. Okay. So maybe I want to save it. Just okay. So I'm going to go ahead and say save. And instead of save it in the Muk3D format, I can actually save it in CAD format, for example, if I want to save it. And that's being saved now. My break lines are reusable. I can do now maybe your fine modeling inside of CAD if you want, or your detail design. As you can see very rapidly, you can do all those volume calculation. I'm going to show you another example. This is just like we build a wall all around this pond. Maybe you want to excavate the pond. So I'm going to show you another example. In this example, actually, so earlier on, I showed you that you could export the data into other formats, but you can also import from various formats. If you look at data imports, we can bring import like data from like a text file. It might be data from CAD or Civil 3D. You might have got more GIS data, or maybe the grids that you have in terms of elevations, or it might be coming from your LiDAR data. So there's a range of data that you can actually import from. So in this case, we'll import from a DWG directly, and you can see that it's read automatically. And instead of just building a pond, with this time we can build an excavated pond. So not only we will build the wall around it, but we'll excavate at the same time. And in this case, I actually want to optimize it. So I want to optimize it in a way that I can optimize my cut versus fill. So I will say I'm trying to build a pond that will be 500,000 cubic meters. I don't know at which elevation the crest and the base will need to be, but I need to give it a first value. So I'll just say it's going to be 105. But ultimately, this value will be computed. It will search for what is my best crest elevation and what is my best base elevation, so that actually the cut and fill is managed. I'm going to say a downstream slope of upstream slope of 1 and 2. Shell height is just for calculation purposes. I'm going to make it 16 meters. And the crest width will be 16 meters. Sorry, the shell height should be larger. I'm going to make it 30. The freeboard, I'm going to make it 2. And the base elevation, I don't know. What are 500,000 cubic meters? Maybe it will be 10 meter deep. It might, I'm not sure. And for the cut and fill, I'm going to say 90% of my cut need to be reused as part of the fill. So I want it to be optimized. So I'll go ahead, I'll give it my crest, and then it will go and search for what is the best crest elevation and base elevation that will give me 500,000 cubic meters. So you see the final result showed me that actually a crest elevation at 102.9 and a base elevation at 97.2 was the best optimized value, so that my cut volume is 190,000 and then my fill volume will be 170, which is about 90%. And it gives me my pond at 500,000 cubic meters. So you'll see, this is now my pond at 500,000 with a 2 meter freeboard. I can remove the freeboard and you can see how we've built it rapidly. So those are some of the structures. I'm not going to go through all the structures that can be built. I will show you a couple of other ones. I'm just going to show you this quick video. So in this case, we've got both the excavation on top and the waste dump at the bottom, and you'll see it's very similar. It's also like dynamic models where you just delineate your crest, and then straight from the crest, you get like a form that you can fill in and change some of the parameters, whether the depths or size of the benches, etc. But it allows you to rapidly like do some of those designs. It's not only excavation and waste dump that you can do additional parameters, like this is all the structures that are available. So we can build excavation, those dumps. We've seen the dams and the excavated ponds, but as well you can build some terraces, which also have some cut and fill, some ditches, as well as some berms and some roads. Once you have these structures, you might want to actually go further into the detail. As I was saying, it's really powerful when it comes to volume calculation. So you might want to look actually in terms of zonation. Same thing, I'm just going to show you a brief one. So you first would go to your zones, and then you create a profile for the various zones that you want to actually build inside of your dam. So now we're building the internal structure of the dam. I'm just going to fast forward it. You define the various layers, and then once you've defined those layers, you can add as well like a blanket layer for some seepage, as well as some liner. Now that's how you build the actual template. Once you have your template, then you go to zones, and then, so I'm going to show you the one that we'll be looking at now. I'm going to load one. And this one is a little bit more complex than the one that just been drawn. So you'll see here, I'm just going to expand that a bit. So in this case, we've got an impervious core here in the middle, and then we've got some sand outside and inside, and you've got like a drainage zone that's actually delineated here. We've got also like a concrete core block at the bottom here. So that's the internal structure of the dam now. So we'll go ahead, I'm just gonna, and build it. So then you take your zones. We've already defined the actual zone model, and then we just say, well, let's calculate it. So based on this zonation model, and based on this crest, it will now calculate all the various areas that needs to be calculated. So you see it's calculated the drainage zone, it's created the drainage zone, impervious core, sand inside, sand outside, and the liner. And then it will show us as well what are the volumes that you require to actually build each of those components. So I'm just going to make it slightly bigger. And you can see here the various volumes that have been automatically calculated. You could potentially reuse that similarly to do it with roads as well. One of my colleagues, Sam, from North America, has got a webinar online. I'll add the link to it. This is just basically what it looks like. So basically, you can similarly define your zones for your road, and then you can also apply it. So very similarly, but it works also. Then still within Muk3D formation, so this is all included within Muk3D formation. You've got also some tools when it comes to do very basic surface water. So one of them is called watershed. And when you use this watershed wizard, basically it just calculates, it expands the possibilities of what this grid can do. So this grid has already been prepared because it takes a little bit longer to run. And then once you have it run, you can just say, okay, I want to generate some catchments. So any catchments that have got an area of 50,000 square meter should generate, oh, sorry, I'm not in the right folder. Any catchment with 50,000 square meter should generate a river. So it will go ahead and create the rivers for me. So that might be useful if I'm doing some siting, for example, for a tailings storage facility or for other structures. And automatically that network has been built. I might want to do additional things with it. I might want to, for example, generate a catchment and automatically get this catchment. So I'll just go ahead. Just need to be on the actual line. And it will now calculate my catchment, and the catchment will be calculated. It will create a surface for it, and then the area has been automatically calculated. There's a bunch of tools that are available. It might be about assessing a distance from a pond to a crest, or there's a number of tools that are available here that allows you to do a couple of very simple and basic hydrology and hydraulic estimates. Finally, there are some tools to do some visualization. As you've seen, all those graphics have been generated straight from Muk3D. You can just edit any imagery to color them based on footprints of various areas. So this has been generated. You can also do some camera animation. I'll show you a couple of animations as we'll go along, but I won't go too much into the details of it. Okay, so now that we've pretty much covered what Muk3D formation does. So Muk3D formation really provides you all the tools to develop a number of structures. Those are predefined structures that you can put inside of like dynamic models, but you can also, because you're constantly manipulating polylines, surface, and grids, you can actually build more complex structures. If you want, just out of like polylines, you can create your own surfaces as well and do more complex structures. And then also, of course, the visualization, the surface water, and also you can do a bit of scripting, but I won't go too much into the detail. So that's what covers for Muk3D formation. Then on top of that, we've got Muk3D Tailings Plus. And so Muk3D Tailings Plus now add the whole tailings modeling on top of it, on top of everything that already existed within Muk3D formation. So really the concept around what we'll try to do here is we're trying to both raise dam, and as we're raising those dams, we're trying to do some deposition. So this is also a video that's been generated automatically from Muk3D. So we will try to both raise the dam according to specific construction, and as we're doing the dam, we're trying to do some deposition. Now, of course, when it comes to the field of like managing tailing storage facilities, one might want to like think that you need to look at the very rheological level, like the fine detailed level. But because of the complex nature of it, it's just impossible, and the sheer dimension of those structures, it's just impossible to do like some rheological model out of it. So the idea is to step back and to look at it at a slope level. So within the beach slope contains all information about the hydraulics and the rheology and the material. And that's sort of like the concept. So I'm just going to show you a small video about what's really is happening. So when we're trying to model with Muk3D, as I was saying, what we'll do is we'll set some tailings property, which will be your beach slope and your densities, and then we'll have some volume that we're trying to discharge, and it will search what is the correct elevations for the discharge and the pond elevation that will give us this specific volume that we're trying to discharge. And of course, according to where you're doing the deposition, we will have different patterns. And once we're done with one run of deposition, we might want to raise the wall to actually increase the containment to do like some further deposition. And it's sort of like a loop like this, where you're trying to manage your containment and start doing some deposition of tailings on your surface. So first step is to define some characteristics for your project. So the first thing that we'll do is we create, you can create some characteristics. In this example, we'll look at a very simple one, so it will be called sand. There's only four properties. It's the density above water, the slope above water, and then the density below water and the slope below water. For the sake of simplicity, we won't be dealing with tonnages, so we'll keep a density above and below water as one. So we'll be moving volumes. So we'll be always talking about volumes, but you could directly enter your densities. And so you can be talking about density, and then it will automatically convert them into volumes. In terms of the slope, there's different type of slope that we can enter. First type of slope is just a linear slope. The second type of slope is a compound slope, which is a bit more complex, where you actually fit it to a specific location. So linear is more like for your greenfield project. Compound will be like you've got an actual site and you need to actually fit it to that specific site. So you will give it specific increments for different distances, and each of those increments will have their own slopes. There are tools available to, I'm not sure if I've got it here. No, I don't have it here. It's here. There are tools available to actually, so I'm just going to take this example of a real case. So really, there's tools if you've got an actual site where you can actually create like a compound slope out of it. I'm just going to make it very rapidly, so it's not going too much into the detail, but it's just to show you as an example what can be done. So in this case, I'll just create a cross-section for my system. You want to find like a representative slope. So this is sort of the cross-section that we'll be looking at. And I'll go to ooze, beach slope, create a compact slope for this line. And here it will just give me, I just need to enter basically some distances, and automatically it will estimate those slopes. So maybe I've got my first 50 meters, and then my 40 meters, and then 30. Then I've got another maybe up to here, so that will be 270. We'll make it 240. And then we might have got another component all the way up to 520, so that's an extra 250 meters or 230 meters. And then automatically it will calculate what is my final slope. So you see it said, okay, the first 30 meters are at 0.03, and then the next 240 meters are at 0.008, and then the next 230 are at 0.0004. And then out of that, I just say, okay, create a tailing. I've got already one that's called slope fitted. I'm going to reuse this one, and that corresponds to my slope above water. Maybe I've got like a bathymetry, in which case I can actually do also the slope like below water. So I'll just click on OK. And if you were to go back to our database of tailings and you looked at this slope fitted, you would find now that we've got our slope that's been automatically estimated here. So now we've done with setting up some tailings characteristics, we can start, and we've learned earlier on how do we build various containment. Now we can start with doing the deposition. So to do the deposition, first step, we need to have either deposition points or deposition line. So I want to use this grid. We will start doing a discharge line. So we'll go to structure ooze, and then so then I just need to let someone in. So now we'll go to ooze, and then discharge points, draw regularly spaced discharge points. And we'll say, okay, I've got my dam crest, which is at 115 meters. So I'm going to put a discharge line at 114 meters. And is going to put discharge spigot. Is going to be a spigot line. So we'll put discharge points every 50 meters. And I'm going to go ahead and put my deposition. I just need to put those points here. I'm going to do it fairly roughly. I don't need to go too much into the detail. And now we've got a deposition line. So though I've only put 4 points in here, it's actually created multiple points every 50 meters. So I can put some annotations to it. So I'll just put some marker just so that you can see where are our deposition points. So you can see that we've got now deposition points all around the perimeter, or at least in these sections of the perimeter. And we want to save it. So let's go ahead. I'm going to set that as my working directory, and I'm going to save this discharge line. I'm going to call it discharge line. And so now I've got a discharge line. I've got a containment. We've created tailings characteristics, and we can start doing some deposition. To do the deposition, there are multiple algorithms available within Muk3D that allows you to do the deposition. The first that we'll be looking at is called capacity building models, where really we just give it a specific elevation and we just fill it up to that specific elevation. As you can see, you can have maybe, for example, as drawn, where it just like it takes you points and then it just look at the slope based on the points that you've given. You might have got contours in basin, in which case you don't even need to actually provide a discharge line. It will just discharge all around the perimeter. So you just give it a specific containment, and then automatically, given the elevation that you give, it will automatically create it for you. User flow path is more adapted for like your single discharge points, maybe like a valley discharge, for example. It might be like the discharge of a path that of a pipeline that you're actually pulling. So you give it a direction, and then it will take the elevation at along this line. The one that I use the most is called flow path downslope. Flow path downslope mimics a bit the drops of water, so it will take your discharge points that you have. It will mimic what a drop of water would do, the path that it will take. And then when we do the deposition, the model will search at which elevation you're trying to do the deposition, and then it will search along that path to actually do the discharge from these specific points. Another one is called vertical. This one is quite good for central discharge. So as you see, there's multiple algorithms available that suits for different type of deposition or type of structures that you're trying to model. In this case, I'm going to start with something simple. I'm just going to do ooze, single stream deposition. I need to select one thing that we just looked at was the deposition model, but you also need to decide on what is the pond model. So are we just modeling like a single pond? Is it a pond which you know has a specific volume? Me coming from like a background in water management and doing a lot of water balances, this is something that I use quite often. But maybe you've got a penstock and it might be based on a pond elevation, or you might have got a specific, it might be acid generating tailings, in which case you might want to have like a specific cover of water on top of your tailings. So you define how you want to model your pond and how you want to model your tailings deposition. In this example, we use fixed pond volume, and we'll use the most basic model, which is just as drawn. So it will take all the points that we've defined here, and it will just do the deposition from those specific points. So we need to select our grid. We need to select our discharge line. For the discharge, I'm going to use that sand, which is a very basic one. It's just 1% slope on top, and then 3% slope below. Above water is 1% and 3% below water. And then I need to put a pond volume. So the pond volume will be 50,000 cubic meters. Initial pond elevation, I don't know at which elevation the pond will be. I just need to give it a first guess. so long as it's below my crest, which is at 115. But the model will iterate. Remember, we looked at the iteration. It will search for what is the pond elevation that will give us, given that we have different slopes, what is the pond elevation that will give us the, what is the volume that we will get? What is the pond elevation? Yeah, let it run, and then we'll see. So we select our pond. So we select a point inside of the pond, and then now we'll start doing the discharge, and it will find what is the correct pond elevation, and that will, so here we almost completed, and we can see that we have now, so still running. It's creating all the various files. It saved them automatically. You can see now we've got our results are plotted here. So I'm just going to show you all those results here. So you see we were able to deposit a total of 7.6 million cubic meters of tailings on this area. I'm just going to clear those annotations. We don't need them anymore. So this is what our tailings looks like once we've deposited at an elevation at 114. And I'm just going to put some contours on top of it so that we can see the various deposition. So the various contours. I'm going to make it at 0.5. Okay, so now we can see we've got our 1% slope on top, and then we've got our 3% that is below water. So we looked at a fairly basic example. It gives us the total volume that we were able to deposit, which was 7.6 million cubic meters. We've got our pond at 50,000 cubic meters, and it corresponds to an elevation of 110.2. So it iterated to find what is the correct elevation given the slope that we provided. But maybe we're not trying to deposit 7 million. In this case, we will use like a capacity model, which we're just trying to fill it up until a specific elevation, but we didn't provide a specific tonnage or a specific volume. So maybe in the next example, now we'll just do the same, but this time we want to provide it a specific volume. So we'll go ahead and say we want to do a single stream deposition. We'll keep pretty much everything except that we'll use a different model. Early on, we looked at those fixed elevation models, which correspond to capacity models. And this time we would just want to see, well, actually, let's deposit 5 million cubic meters. So let's go ahead. Same thing, we'll take the same grid. We'll take the same deposition line. Initial deposition, I'm not sure at what elevation. I'm going to say 110. I'm going to reuse the same tailings. We said we want to deposit 5 million cubic meters of tailings. And for the pond, we had 50,000 cubic meters, so we'll keep the same characteristics. Though the pond was a bit small, but it's fine. So just for an example, and then I don't know what elevation it corresponds to, but I need to give it a guess, and the maximum is 115. This is the crest elevation. So this time we provided a specific volume. And now it needs to iterate over two things. It needs to iterate over what is the pond elevation and what is the discharge elevation that, given the slope that we provided, will give us the correct geometry. So it will iterate, and you can see it iterates over both a pond elevation and a discharge elevation. And now I just finished computing. It will save a whole lot of files which correspond to all the files that have been generated for this deposition run. And that's it. So that's run. And you can see this time when we try to deposit 5 million, so we've got our 5 million cubic meters. The discharge elevation is not at 114. Because for 5 million now we need 100. The discharge at 111.004, and the pond elevation is at 107.3. Okay, so now we've learned to do the deposition. We can we've only looked at a single stream deposition. So we've got a single deposition which gives us one discharge elevation. We might want to do it more complex. We might have got different discharge lines. We might have got different, so in this case, we'll look at an example where we've got a deposition line here, and then we've got two deposition line in from the valley. So this time we'll use this multi-stream deposition. I'll just like fast forward it because of course, as you adding more deposition lines, it takes longer to actually run. So for the sake of this one, so we've got two different type of deposition. The first one will be flow pass downslope on the dam wall, and then at the back in the valley, we'll have a single discharge deposition. We'll deposit different type of tailings, so it could be the same discharge line, but you've got different tailings that you're depositing. And so in order to mix those various flows, we can also split it into different divisions. So in this case, we'll put 12 millions in the wall, we'll put 3 million in one of the branch and 4.5 million to the other branch. Same thing, we don't know what are those initial elevations, so we just need to give it a guess. And then we'll subdivide it, so meaning that it will start putting 1/3 of the deposition in the wall, then it will go to the first branch, to the second branch, and it will keep on coming back. So you could subdivide it more times, and that will allow you to kind of like look at the interwoven burden. So the mixing of the various flows. So this is just fast forwarded because it takes a little bit longer, and for the sake of this presentation, I just recorded it just now. So now we've run it, and we've got now multiple discharge elevation for the wall and then the back end as well. You might have every single spigot points might be modeled individually, but of course every time it adds to the time that it takes to actually compute it. But you can always go into that level of complexity. So now we've learned how to, from a containment, prepare the site with discharge lines and tailings properties, be able to do your deposition. Now you want to actually start planning. So you want to start raise your dam with specific characteristics. And so for that, you've got what's called like dam templates. So dam templates are a tool that's provided within Muk3D. Here are the different templates that exist. And basically you set up your templates, which are physical characteristics about your dam. You set up a reference line. So for example, in the case of a single stream, the downstream toe is always the same no matter what. And once you have it, you just need to give it an elevation, and automatically it will build according to this specific type of construction. So you see, those are the templates that exist. I'm just gonna run one quickly. So I'm just gonna create only the shells at this stage. So those are templates that have been already created. So I'm gonna say it's gonna be an upstream crest, and I want to actually raise it at different elevations. So I'm gonna say I'm gonna run it at 110, 115, 120, 125, and you can see here it just created only the shells, but you can see that the shells have been created according to that template. So typically you would raise your dam, you start doing some discharge. Once you don't have sufficient freeboard, then you can raise your dam on top of your model, and it will use this specific template. So you don't need to actually try to manually kind of like retrofit it. It automatically does it for you. So I'm just going to show you an example here. In this example, we'll start with this configuration where we have a dam where we started doing some deposition at 105 meters. And so then we'll go ahead and go to ooze project. We'll do a new deposition run. This will be called demo. And we'll now move it to 110. So we've got a dam we've done some deposition on top of it. Now we want to raise the dam. So we'll go to our dam template. Dam, we'll raise the dam. This time we'll use the same templates, which is called upstream crest. The new elevation is called 110. It's at an elevation of 110. The grid will be from the previous run. So in this case, 105 output grid, which is once we run the deposition, and we'll generate some discharge points for it. So you see now it will automatically do the raise on top of it. I could just do a cross section through it so that we can have a look at it. So now we've built our dam on top of it, and it's already at 110. And then we would go ahead. So we would go ahead and then fill it up with tailings and then carry on and doing that manually. So manually, you can start doing your planning like this, where you go bit by bit. Every time you do your raise your dam, fill it up with tailings. Maybe you carry on doing several runs of deposition. And at some point, you need to have more containment and you carry on raising your dam. There are additional tools. So this is like the most manual way to do your planning. You also have some auto staging. So auto staging, the way it works is you have a grid, you have a base, the toe of your dam, which is located here. I can show it to you here, so it's below. And auto staging does it kind of like for you. So it's really for fairly simple systems. So let's say, for example, we wanted to do, I'm going to do it a fairly simple one. So I'm going to say it's going to be a crest width of 20 meters, downstream slope of 1 in 3, upstream slope of 1 in 2. We'll stick to the same tailings characteristics, which is sand. We'll say, okay, we wanted to start at 105. And every 4 meters, we want to start raising our dam by stage, like by 4 meters, all the way up to, say, 125 meters. Discharge points will be every 150 points, every 150 meters. Beach freeboard will be 1 meter, and we'll go ahead. So I'll select my grid, I'll select my, and I just need to select a point, and then it will go ahead and do the discharge for me. So now it's done it. I can have a look at, I forgot to, where's my folder? Oops, okay, I put it in the wrong folder, but it's fine. We've got a summary of everything that's been calculated. So automatically it raise the dam to 105, fill it up with tailings, raise the dam to 109, fill it up with tailings, etc. And then it gives us all the results. So it gives us the result in terms of, for each elevation, how much you needed to actually build your wall, and then how much tailings you could put for each of those phases. There's a couple of more things I want to go through. So very quickly, because we're running out of time. So that you could ultimately automate it, and you would automate it by creating a small script for it. I'm just going to show you an example here. And in this script, I'm basically raising the dam, fill it up with tailings, do a bit of visualization, and then at the end it will create like a... So I've already pre-programmed inside of a Python script, so you can record macros. There's a button here to record macros, and basically it records the commands that you use. And then once you've set your commands, so in this case, raise the dam, fill it up with tailings, edit my imagery, and then you say, okay, in my Python script, let me put it in a loop. So I want not only to do it once, but I want to do it for several times for multiple elevations. And so it will do it for you in a very systematic way. So this is a good way when you're trying to do your planning now and you have to repeat the tasks. And so in this case, once you have it set it up, it allows you, like, you don't have any errors. It's, of course, it's a lot faster to actually all of those things. So you see in this case, it raised the dam, it did it multiple times. And at the end, it's going to create a small animation for the sake of the presentation. This is fairly low quality, but if we had a bit more time, of course, we could do something that's a bit better quality. Last thing, when it comes to Muk3D Tailings Plus, we've got dam break analysis. So typically for dam break analysis, I'm just going to show you. This is really for fairly high level. So same thing as I was mentioning early on when it came to rheology. When it comes to dam break analysis, doing a full-on computer fluid dynamics simulation can be both time and financially consuming. Not that it shouldn't be done, of course, but it's very limited in terms of its scope. You can't run like multiple analysis. What Muk3D provides is really to do like rapid estimates, and those estimates are those three main things. It's estimating what is the breach volume. So if you had a specific breach with a specific failure slope and given a specific elevation, what would be the volume that would be breached? If you had a specific failure slope, what volume would be mobilized? And then now that you know the volume mobilized both from your tailings and your dam wall, given a single slope, what would be the run-out distance? So you estimate both very rapidly what is the volume that would be breached, what is the volume that would be mobilized, and then how far would it go? The big advantage of that is that you can analyze very rapidly and assess what sort of range are we talking about. So in this example, it's a fairly rapid example, a low quality grid as well, just for the sake of timing. Just dam break. And so, for example, you could say, I want to breach my dam. And I'll say I'm going to have a runout slope of 1.5%, a failure slope at 2%, a breach width at 50 meters, and a breach elevation at 115 with a dam failure slope of 1 and 2. So it will ask me what is my various grids, what is my breach, where is my breach happening, and very rapidly, you see now we've got the breach, how much volume would get mobilized, and all those volumes are available here. And what would be my run-out distance. I'm going very rapidly through it. Of course, there's a lot more tool, especially around sensitivity analysis in terms of testing with various slopes, testing with various properties for the breach very rapidly and estimating those at several levels. This covers for Muk3D Tailings Plus. I'll go very quickly under a Muk3D simulation. So as I was mentioning, Muk3D simulation now combines coupling Muk3D Tailings Plus with either Excel or with GoldSim. So typically, a lot of the tailings plannings are happening in terms of the mass balance are happening in a spreadsheet. And so people are used to working with spreadsheet. That's why you can have like all your sequence of events that might be happening. It might be what is the deposition that you have every single month. And you put all your scenarios in here. That creates basically an interface that Muk3D can read. So it will read the inputs, process them inside of Muk3D for one specific month or year or quarter, depending on the sequence that you're trying to model. And then it will populate then the outputs. So what it does is it takes the inputs straight from a spreadsheet, use them inside of Muk3D, and then populates the outputs. So this is sort of like once you run it, I'm just going to show you the video for it. So when you run it now, it takes the inputs, runs it in Muk3D, and you see it start populating them. So now you can do like for various sequencing. So not only you're doing like for one single deposition, but it basically allows you to manage all your inputs and outputs in a spreadsheet. Therefore, you can also like change the spreadsheet and save various scenarios and run your scenarios straight out of your spreadsheet. This is a fairly simple example, but I've done like simulations that are like really complex where you really define how you're modeling and the various operations at different stages in quite a high level of complexity. Similarly with GoldSim, except that for GoldSim now, on top of having fixed inputs, GoldSim add a layer which is around, well, we can now also look at more complex detail because now we can use like distributions as well. So in this case, it's an example that I will just show you in a video where we're running a water balance at a daily level. And then on top of it, we're doing a mass balance in Muk3D at a monthly level. So every single day, GoldSim runs it. At the end of the month, it sends data for what's going to happen in the next month in terms of tailings deposition based on specific distributions. Muk3D will do the runs, and then it will export a new state storage capacity so that it can be adapted for the water balance modeling in the next months, etc. So this is when the model is run. So of course now it takes a lot of time to run, because now you're processing not only, let's say, 5 years of simulation that you're running every single day at a water level, but also monthly in terms of deposition, but you do that multiple times because we want to assess multiple futures, and each of those futures give us different results. The big advantage of something like that, I'm going to show it to you, but I just need to see it open. The big advantage of something like that is that now when you look at results, so here is the results for your crest level in red, and then you've got a various water level for your elevation discharge and your pond elevation. But every time that you model it, it gives you different results. So that when you look at it from a probabilistic perspective, well, you're not just saying that you need to have your dam raised at 420 meters in July 2026. You said that it could happen as early as late 2025 or as late as mid 2027. So yes, you might be prepared for that, but you might want to actually have some contingency plans for what happens if you got here, or also potentially delay capital costs further if need be. So it allows you to kind of like look at it from a risk perspective. And this concludes this live demo of Muk3D. If you want to know more information, go to the muk3d.com website and contact your closest reseller. That's it for today. See you next time. Shop shop.